Okay, hello to everyone, and welcome to this webinar of how to optimize the number of modules per string in your PV plant. Now I would like to give a couple of minutes just so that everybody attend the meeting, and after these 2 minutes we will start with the webinar. I will now mute myself and just wait a couple of minutes. Okay, so now I think that we can start after these 2 minutes. I believe that most of the attendees are now here with us. Well, first of all, I would like to say hello to all of you and welcome you to this webinar in which we are going to speak about a way of optimizing the number of modules per string or the string sizing in your PV plant. I hope you enjoyed this session, and here we will speak about these 4 main points. The agenda first, we will start with the importance of the string sizing. I will try to explain a bit of the most important aspects with regards to this string sizing, where the amount of modules that we connect to build one string affect more to the PV plant and to the main aspects of the PV plant. Then I will continue with a review of the 2 of the main standards, to IEC and NEC, and we will see how those standards suggest to calculate the number of modules per string. Then we will go through one use case that I have prepared to try to explain how can we optimize the number of modules per string, taking into account the main considerations that we will see in the 2 first points. And then we will go through the question and answer time, in which I will try to answer all the questions that you may have during the presentation. If you have any question at any moment, please do not hesitate on writing them in the questions section. They will be saved there, and then at the end of the presentation, we will go through all of them. Well, before going through all of these, let me present myself. My name is Álvaro Pajares. I work here at RatedPower as a project and software engineer. I've been working here now for almost 2.5 years. And basically, I work like helping to define the energy engineering requirements of some of the projects that we are working on for pvDesign, the product that we have in RatedPower, and also in some of them working with the coding part and developing these new solutions. So with that being said, let's go to the first point. I would like to briefly speak about the importance of the string sizing and what aspects of the PV plant are affected by this. First, we can see this schema where I have tried to explain that, as many of you, I guess, may know, modules normally are connected in series to build one string when designing a PV plant. Then these strings will go to the inverter. Beforehand, there may be also some collector devices in terms of central inverters normally, DC bus, combiner boxes, or others. But here I wanted to highlight how the size of the string will determine the voltage of the DC side. So depending on the number of modules that we connect in series, we will have defined the voltage of the DC side. When we speak of the low voltage system, this will affect different parts of the plant. In terms of cable sizing, the voltage that the string has will be affected by this. Also, the current that will be flowing through this string cable. So we can say that depending on the number of modules that we are connected in series, the cable sizing will be directly affected, and how increasing this number of modules per string will normally simplify the size of the cables that are going to be defined. Also, if we want to have a certain DC power for one inverter, if we increase the number of modules that we are connected in series for one string, we will be also increasing the power that is related to that string. So that means that we will need less strings for the inverter, and so we will be decreasing the number of cables that are required for the same DC power. That being said, we can conclude, let's say, from the DC side perspective, if we are not considering anything else, that if we increase the number of modules per string that we are connecting, we will have, let's say, less complexity in the low voltage DC system, and that the DC system will be better defined. Also, it's worth mentioning that some of this equipment will have some limitations on the voltage that they accept, that normally will be given by the manufacturers. So that's also a limitation that we do not want to exceed, as we don't want to damage any equipment from the low voltage side. If I go to the following slide, here I wanted to highlight the importance of the DC voltage at inverter level. First, what I have mentioned, that if we have a very high low voltage, we may be damaging some equipment of the PV plant. So it's very important to confirm with the manufacturer what's the maximum voltage that they accept, and try to be always below that value, because if not, we may damage the equipment. And then in terms of inverter, the first picture is trying to represent an operation window of one inverter. This operation window is affected by a minimum and a maximum voltage, and also by a maximum and a minimum power. So the power is related to the DC oscillator that we are defining, so that will give us some losses due to the power. And if we go to the one related to the voltage, this one is directly related to the number of modules that we connect to build one string. And we can see here that if we are not reaching the minimum voltage that is given by the manufacturer of the inverter as the minimum in which they will give us, let's say, the best performance of the inverter in terms of MPPT tracking, we will be losing some power that is not going to be produced by the inverter. That happens in both sides of the minimum and the maximum. If we are below the minimum, we will be losing some power, and we will have like one loss related to the inverter voltage threshold. And if we go above, we will be losing also some power, and we will have one loss that is related to the over voltages. Then I also included one picture that comes from one manufacturer. It's one example on how the inverter efficiency is also affected by the voltage that is reaching the inverter. We have in different colors different voltages, and we can see how while we are increasing the voltage of the DC side of the plant, we are decreasing the efficiency of the inverter. It's also affected by the power, but we can see that here there's a relation with the voltage. So with these two things being said, we can conclude that when we are trying to define the optimal string size for one of our designs, we have here like a kind of a trade-off, because we have seen that we want to be within the operation window of the inverters, and we also want to have the maximum efficiency of the inverter. So we want to be within those ranges, but also we want to reduce the costs and the complexity of the low voltage DC system. So we will try to define as many modules per string as possible to try to reduce that complexity and improve the design. Apart from this, we also have one limitation where the low voltage equipment will have a maximum voltage, and if we are above that value, we may damage the equipment and we may have some problems in the plant. So it's something that we will try to avoid at the moment of the operation of the PV plant. So with that being said, now we are going to the IEC and NEC standards. I will try to explain here the main things that they say with this regard in terms of calculating the string sizing of the plant. From the IEC, we have two, one which is from 2016 and the other one which is from 2018. If we go to the older one, we will see that they suggest that when calculating the number of modules that can be connected to build one string, we must consider that each of these modules that compose one string is working at the open circuit voltage being corrected with the lowest ambient temperature. So it's like the most restrictive one because they are considering the highest voltage of the module and also that it's working at the lowest ambient temperature. It's also like the most conservative and the one that is going to for sure give us a voltage that never exceeds like the maximum voltage of the DC system. Then the IEC from 2018 explains that we must also consider that open circuit voltage when calculating the maximum number of strings, but being discorrected with the lowest ambient temperature, but being limited to sunlight hours with a threshold of 10 watts per square meters. So they give this a small threshold so that when we take into account that lowest ambient temperature, we are sure that there's some radiation also reaching the modules. Here, this IEC also includes some information about the fact that we must ensure that always the number of modules that we have connected building one string are always within the MPPT range. So they give us like a suggestion saying that when calculating the number of modules per string, we must have also a lower limit, considering that the inverter is working at the lowest voltage within the MPPT window, and that the module is working at the MPPT condition. Then last, we have the NEC 2017, where they explain that the maximum number of modules that we can connect to build one string must consider also the modules working at open circuit voltage and being corrected for the lowest expected ambient temperature. So it's like the same that we were finding in the first IEC standard. Here, apart from this, I would like to highlight that they also suggest that some cases with engineering justification being also in accordance with the manufacturers and the local authorities may have values that are exceeding this value, this maximum number of modules per string, but those must have like the engineering justification to ensure that we will never be above the maximum voltage of the system. So with that being said, I would like to open this poll and ask you, what method do you normally use to calculate the number of modules per string? Here we have seen these three main standards, the IEC and NEC standards, but we also know that there are like many other methods that can be used to calculate this value, considering like more metadata and different points and what's the specific case that we are expecting from the metadata. And well, we have opened this live poll. I also think that when designing a PV plan, it's very important to spend some time when deciding what's the number of modules that we want to build one string, because it has it affects many parts of the plan. And I believe that it's a parameter such as maybe the DC-AC ratio or the pitch distance that are very important to consider when designing a PV plant. Okay, so being back to the presentation, now it's show time. So I would like to present you a use case where we are going to see a way of optimizing the number of modules per string, and how can we find the best solution for our specific design. So here we can see how pvDesign give us some recommended values for the number of modules per string that can be defined. We will give you an upper and a lower limit. The upper limit will consider the restrictions that were being defined by NEC and IEC. So we are going to ensure that the string will never exceed the maximum voltage of the system when correcting the modules at open circuit voltage and being this corrected by the minimum historical temperature. Apart from that, also the maximum number of modules that we recommend must ensure that the maximum MPPT inverter voltage is not exceeded when modules work at the standard conditions. Apart from that, for the minimum number of modules per string, we will give a lower value that must ensure that the minimum MPPT inverter voltage is reached when modules work at the highest historical temperature. So this will be like the worst case scenario. And so this way we are ensuring that inverters will always work at its best, whatever is the condition that they face within the operation. So that being said, here we have this case study that I wanted to evaluate. I have defined a design with modules of 500 watts and a central inverter of 2000 kVA, and a case where we just are going to evaluate one inverter and a DC-AC ratio of 1.2. I have evaluated different scenarios with 20, 23, 24, 25, 6, 7, 30, and 32 modules per string. I have defined these two in red, just because if we go to pvDesign, and we look at this specific case, here is where we can define the modules per string. It will consider the meteorological data from this specific location. We are going to recover from different databases the meteorological data. The minimum historical temperature is going to be taken from there. And according to the module, which in this case I was saying 500 watts, and the inverter that I have selected, we are going to have these recommendations for the modules per string. So it's saying that if we have a value within this range, we must be always within the MPPT window and never exceeding the maximum voltage of the DC system. So that's why I have included two additional values of 30 and 32 modules per string, but these are in red because with those values we will then be ensuring that the voltage of the DC system is being respected. So with this case study, I have included like three different objectives. First, to find what's the best string to maximize the specific production, then to minimize the cost of the DC system, and finally find like the best string combining these two main objectives with the LCOE. So we will try to minimize the LCOE and see what's the best solution for this specific case. To do this, we are going to use two different tools from pvDesign, the cloning feature and the comparison tool. And well, with the cloning feature, what we can do is that we can duplicate one design that we have already created with pvDesign, make a small modification and run it again to create a new design. And with the comparison tool, what we can do is that we can put many designs together so that we can find the best solution for one specific parameter. So in terms of maximizing the specific production, I'm going to go back to pvDesign. And if we click on compare, we will have all the designs that we have already created. I did it previously with the cloning feature, and we can sort them by a specific production. So if we are trying to find the best design in terms of a specific production, we will see that the best number of modules per string to be defined is 23, and we may be a bit confused because normally we say that the best value is the upper one, but in this case we are having like the lower value from the range that pvDesign was recommended. This is just for the specific production, and if we go in more detail to the losses that are affecting each of these designs, we can see here that all the designs were having a 0% of losses when going to the inverter voltage threshold, but with 20 modules per string, we were having a 10% of losses. So that means that we were not reaching the minimum MPPT voltage of the inverter, so we were not optimizing the inverter production and losing some power. And then if we go to the efficiency loss of the inverter, we will see how, as we were expecting from the manufacturer's picture, as we increase the number of modules that are connected to build one string, the losses due to the inverter efficiency are also increasing. And so that's why 23 modules per string is the design where we are not having any loss due to the voltage threshold. And also with 23 modules per string, we are having like the best efficiency of the inverter when being compared to the other designs that had no loss neither for the voltage threshold. Then going to what's the best string size to minimize the cost of the DC system. I have also gone through all of these designs. For each of those, pvDesign is going to give us some documentation to download with many different aspects of the PV plant, from energy production to cable sizing, substation, and many of them. And I have gone through the listing of cables, where all the cables from the PV plant are going to be defined, and the bill of quantities, where we are going to summarize all the cables also from the plant. And going back to the slides, we can see, as we were expecting, that as far as we are increasing the number of modules per string, the total length of the string cables is being reduced, as less cables are going to reach to be defined also to reach the inverter, as the DC power is similar. And then how the size of the strings is also being reduced as we increase the number of modules per string. Cables with 10 square millimeters are being reduced, and smaller cables appear with high modules per string. Then, lastly, here we have the comparison with the LCOE. To minimize, to test the LCOE, what I have done is that in pvDesign here we also have the possibility to evaluate the costs of a PV plant. And to do so, depending on the country in which we are working, in this case it was Spain, the location of this parcel, and pvDesign will automatically give us information about the prices taken from the IRENA with different countries. And in this case for Spain, I have taken these values, but I have added some entries that affect the string cables with prices that are directly related to the meters that we have of string cables, as the other entries were defined according to the main peak power and will then represent currently like the price of the strings. So going back to the comparison tool, if we sort them by the LCOE, we will see that the best solution will be the the design in which we had defined 27 modules per string, and it was something that we may have expected as it's like an intermediate value between having the best solution in terms of low voltage DC system, in terms of reducing the number of cables that we are going to include, but also in terms of optimizing the production of the inverter, and it's a value in between that, let's say, balances both options, and that will be like the design in this case that is optimizing the LCOE for this specific design. So with that being said, now we can see the results of the poll that we were giving before. And here we can see how most of our users, our attendees, use the IEC, the first option that we were defining, and also that big percentage, the 19%, will give also will use a different method to calculate this number of modules per string. So it's quite interesting also because two of the options that were having more votes, IEC 62548 and NEC 2017, are the option that actually we are considering for pvDesign. And well, it's quite interesting also because it's normally it's the solution that will then for sure exceed the maximum voltage of the PV plant, and is the most conservative one in my opinion. So then now we can go directly to the questions. So I will go to the questions that you have been writing during the presentation. Also, if you have any additional questions, this is the moment to do them. 1 second. So Manasa was asking if the graphs that I was showing are from pvDesign. So here we have in pvDesign this comparison tool. These graphs were from pvDesign. Also in the comparison tool, we will have different graphs that represent different parameters of the designs that we have generated. For example, for the LCOE here, it's represented directly from the graph, and also the capex of the plant. We can see them all here. But these specific ones, the values that we were having are taken from pvDesign. So the losses were taken from this specific for each of these designs. So the energy, for example, in terms of inverter voltage threshold, this value is given by pvDesign, also the inverter efficiency. And I have put all of them in a graph to represent them. So the values are from pvDesign, but these specific graphs are like not directly taken from pvDesign, let's say. Okay, so from Srikan, sorry if I do not pronounce well the name, was asking about the DC line losses that can lead effectively to a voltage drop before reaching the inverter, especially with virtual central design using string inverters, and if it can be considered when calculating the string length with pvDesign. So the answer is yes, pvDesign, when sizing the cables of the PV plant, we will consider the values that the user is defining here in the cable sizing tab. So first of all, we have different standards that can be considered for the cable sizing. Then what's the maximum voltage drop that we want for the DC side and for the medium voltage system? So this will be directly affecting what you have asked here. And then for each one of the different levels that we have in the plant, the string cables, the cables that will go through from the string box to the inverter, and then the medium voltage cables. We will have different options that we can modify. So the sections that we want to evaluate, number of cross sections that we want for each level. So if we put a 2 here, all the string cables will be sized with just 2 sizes of cables. Then the maximum circuits per polarity or per phase if it's AC voltage. Then the material that we want to use, the insulators, the cores, and if it's the sunlight is barely reaching the cables or not. So when sizing the cables, we are going to consider that. And for each one of the cables, if I go to string cables, for example, we are going to find different sections for the 3 criterion that we consider. There it is. For the maximum ampacity of the cables, we are going to find what's the load current that each cable has, the sizing current that we are considering according to the different factors that are affecting each one of these cables, the ambient temperature, soil resistivity, and ground temperature. There's no sense here because those go in there. And then the grouping factor, also the table in which we can find those factors. And with that values, we are going to size the string cables, the section that is needed for this specific string cable. And then for the voltage drop, also according to what the user has defined, we are going to divide the DC side into the different levels, like the string cables, also the cables that go from the string box to the inverter, and with that calculate the voltage drop that is accepted for each one of these levels, and also calculate what's the minimum required section for this specific voltage drop that we have defined, and then find the cross section that will for sure respect both criteria. So then Kai asks about how many years back would you recommend to get the minimum historical temperature. So here, what we are considering is that it's a typical meteorological year. So it considers like different years and converts that into a typical meteorological year with what's the minimum historical temperature. Here it's a bit tricky, the question, because it's also what direction are we going and how risky we want to be with the number of modules that we define. In my opinion, typically I wouldn't go like to the minimum in all the years, but in a typical meteorological year, I think that is more than enough to be sure that we are not going to exceed this maximum voltage that is accepted by the low voltage system. And also here, I would like to comment that apart from that minimum temperature that is taken from all the days of a typical meteorological year from this specific meteor data, we also provide different values for different irradiances, so that if somebody, for example, wants to consider the case of the IEC 62738, which they were saying that they will take the temperature but considering only sunlight hours, we can come here and see that this is 0.8 degrees. Put that in this box, and this is the temperature that we are going to use for calculating the limits of the number of modules per string. In this case, there's no modification, so with both options there's not any meaning on going one module up or down, so it will be the same recommendations. But if we go to a much higher value, we will see how this value will be modified because it's considering the value that we are defining there. So for maximum string voltage calculation, how would you account for reduced panel output due to aging solar panel? So here, for the maximum string voltage calculation, we will consider like the worst case scenario, which could be like the one that is taken directly from the voltage at MPPT conditions. Regarding the aging solar panel, what we are considering also in terms of losses is that we have the degradation that one module is suffering for the years. So the first year degradation, and then the degradation yearly, and this will be directly taken into account with when calculating the energy production. So, okay, also Manasa is asking if the inverter is with 2 MPPTs, if we can connect 4 strings using a B cable. Okay, so this will be one case that we can use, because if we are, for example, let's go to, I'm gonna put, for example, that we have 2 strings per structure in this case. And if I go here to electrical, and we are assessing the cables with each grouping, we can include what we call the harness. And this way we will be defining like the strings that are within one structure. We are connecting them to a harness system, and this harness will be connected to the inverter. So this way we can reduce the number of inputs that are reaching the inverter. And yeah, then regarding how are the values of the typical meteorological year calculated, if it's an average of 10 years back or else. As I certainly do not really know the correct answer, but I will also like suggest you to go to the knowledge base that we have in RatedPower. From here, you can go to the energy yield methodology, where we do not only provide information about how do we calculate the energy production within the software, but also you will find information about the parameters that we are using as an input. So here you may like have more information about the typical meteorological year and what's like the meaning of this data. I don't see any other questions. So let me check again to be sure that I'm not losing any. Yeah, so we don't have any additional questions. So I think that we can close it here. Many thanks for joining the webinar. I hope that it was useful to you, and well, hopefully you find some interest in it. And if you have also any additional questions, do not hesitate on contacting me, and I will try to also answer you. So many thanks, and hope you have a good evening or morning, or depends on where are you from.